in continuation of the osmosis and osmotic pressures of the solutions, today I like to give a lecture on the derivations of this Vent-Hoff equation thermodynamically using the concept of this chemical potential. Here you can see the arrangement for the osmosis. The solvent is separated by the solutions by a semi-permeable membrane. Solvent is separated from the solutions by a semi-permeable membrane. Semi-permeable membrane will allow the solvent to pass, but it restricts the solute to enter or pass through this membrane. Here these are the two pistons, and the pistons are at the same pressure P0. P0 may be taken as this atmospheric pressure, and the temperature is T at which the derivation is considered, or you can say at which this experiment is being done. And this solvent I have shown in my last class. Solvent is having a high chemical potential, then the solvent in solutions, and this unbalanced chemical potential on both sides of this membrane drives the solvent to flow from solvent side to this solution side, and this is the osmosis. But if we apply a certain pressure called osmotic pressure, so that the flow of this solvent is prevented or is checked up and this osmosis stops. This pi is the osmotic pressure. So we have the three variables you can consider in this experiment. One is pi, osmotic pressure, and the temperature, and you see this x1 mole fraction of this solvent in solution. Mole fraction of the solvent in solution is directly related with this concentration of this solution. So these are the three variables. But all these three variables are not independent, and if we look at this phase rule derived by William Gibbs, American scientist William Gibbs, then we can have this F equal to C minus P plus 2. This is the phase rule, and in this case F is the number of intensive independent variables like the temperature, pressure, concentration, etc. And this C here, the number of components. Here the number of components for the system is 2. One is solvent and other is solute. So C is 2, and the phase. In the system there are two phases. One is solvent phase and other is solution phase, and they are, each of these two are homogeneous in itself, separated by a definite boundary, and so this P also 2 plus 2 equal to 2. Means out of these three variables, only the two are independent variables, and the third will depend on the magnitude of these other two. So we like to have a relation between these three variables by using the concept of this chemical potential of the solvent on the both sides. So pi is the osmotic pressure here, T the temperature, and x1 is the mole fraction of the solvent in solution. So here, since by the applications of this additional pressure pi on from the solution side, the osmosis stops, means the pure solvent and solvent in solutions are in equilibrium. We can write here the solvent in solution at a temperature T and pressure P0 plus phi is in equilibrium with the pure solvent at a temperature T and pressure P0. Means under this temperature pressure solvent remains in equilibrium on both sides of this semi-permeable membrane. So the thermodynamic condition for this equilibrium is that the chemical potential of the solvent at this temperature T and pressure P0 is equal to the chemical potential of the solvent in solutions at this temperature T and pressure P0 plus phi. So we can write here this mu1 chemical potential of the solvent in solution at this temperature T and P0 plus phi is equal to the chemical potential of this pure solvent at this temperature T and pressure P0. If we consider the solutions to behave ideally, means solution must be dilute, and so we can say the ideally diluted solutions for which this Ventov equation is only valid. So this equation, this term would be expanded. This term, instead of this term, we can write mu1 naught temperature T and P naught plus phi plus RT ln x1 is equal to this mu1 naught and temperature T and pressure P naught. One assumptions we have taken here, these solutions behaves ideally. So this relation is written. If we consider the non-ideal solutions, then x1 will be replaced by this activity of this solvent in solutions A1. So if we transfer this term, both are the chemical, this and this, both are the chemical potentials of this pure solvent at the same temperature, but the pressures are different. Here the pressure is higher than this one. And we know the chemical potential is increased with this increase of this pressure over the solvent in solution. So you can, this can be taken here. So or mu1 naught temperature T and P naught plus phi minus mu1 naught temperature T and pressure P naught is equal to minus RT and ln x1. X1 is the mole fraction of the solvent in solution. So the difference of these two is due to the difference of this chemical potential of the pure solvent due to the excess pressure pi. So we know if we connect this one, if we try to calculate this difference between these two, then we have to take this del mu1 naught by del P at a constant temperature is equal to V1 naught bar. This is the thermodynamical relations or the expressions of this del mu by del P at constant temperature, and this is the molar volume of this pure solvent, and this is always a positive. minus positive. So you can see here, if we increase this pressure, then chemical potential of this pure solvent will also increase. So if we transfer, if we have this separations of these variables, then mu1 then d mu1 naught equal to v1 naught bar and dp. Again, if we integrate and also taking the assumptions that this molar volume of this pure solvent does not depend on this pressure appreciably, then this one can be taken outside of this integration, and we have this d mu1 naught equal to v1 naught bar and dp. This one is taken outside of this integration, and the pressure is changing from P naught to P naught plus pi. When the pressure is P naught, the chemical potential is mu1 naught, temperature T and pressure P naught, and when this pressure is like this chemical potential is T into P naught plus pi. So we can, if we do this integration and put this limit, then actually this left hand side is mu1 naught and temperature T and pressure P naught plus pi, and minus mu1 naught temperature T and pressure P naught is equal to this V1 naught bar, and here this P naught plus pi upper limit minus this lower limit, and this one is equal to V1 naught bar into pi. Pi is the osmotic pressure of the solutions which we are considering, whose mole fraction of the solvent is x1. So instead of writing this one could be substituted by this one. So V1 naught bar into pi, and this one equal to minus RT ln. Instead of write x1, it is very usual to express the concentration in terms of this mole fraction of this solute. And we know the x1 plus x2 equal to 1. So instead of x1, we can write 1 minus x2. And if we expand, this logarithmic expansions, ln 1 minus x2, you can write minus x2 and minus x2 square divided by 2 minus x2 cube divided by 3 and minus. Since x2 is much less than 1 fraction, and so since the solution is dilute, x2 is very small, so higher parts of this x2 you can ignore. So you keep the series just after the first term. So this one and minus plus, so this is RT ln x2. So we have got a relation. This x2 is equal to V1 V1 naught bar into pi and divided by RT. This one have kept here in the left hand side is whenever we try to interrelate the different colligative properties of a solution, this expression can be utilized. And now if we change this x2, we like to express this Van Hoff equation in terms of this molar concentration of these solutions. So here this pi into V1 naught bar equal to RT ln here N2 divided by N. This is only x2, and x2, if we split up this x2, then RT and here N2 divided by N1 plus N2. Again, for this dilute solution, N2 is much smaller than N1, so you can approximately, it is the approximations. Former two are the assumptions, and this is the approximation and approximation. So N2 you can neglect in comparison to N1. So this will be equal to RT into N2 divided by N1. If we transfer this N1 here, then pi into N1 V1 naught bar equal to N2 RT. For the case of this ideal solution, the volume follows the additivity rule. So if we apply this additivity rule, then volume of this solution, it is the volume of this solution, volume of this solution which is ideal. So in this case it will be the N1 and V1 naught bar, volume of the solvent, plus N2 and V2 naught bar, it is the volume of this solute. V2 bar naught 2, this is the molar volume of this solute. Again, if since N2 is much smaller than N1, this would be neglected approximately, and this volume of the solutions is this one. So we can write here this pi V equal to N2 RT. Now if we like to come this exactly the Van Hoff equations, then this pi equal to N2 divided by V into RT, and N2 by V means number of moles of this solute dissolved in V liters of the solutions, and this will be the molar concentration. So instead of write this one, we can write pi equal to CRT, and this is the Van Hoff equation. Van Hoff equation of osmotic pressure. Pi is the osmotic pressure, C the concentration which is directly related with this X1, and T the temperature. Now I come to some application of this relation. You know this pi is the colligative property, means it depends on the number of particles, solute particles present in a given amount of a solvent. So actually pi does not depend on nature of these solute particles like size, charge, mass, etc. So this best utility of this relation is application. If we consider the one application of the law of the equation of this Ventop equation, we have the relation phi equal to N2 by V into RT. But N2 number of moles of solute is equal to weight of this solute in grams divided by molar mass of this solute. So if we replace this N2 by this one, then pi equal to W2 by N2 into RT by V. Or we can say this molar volume N2 equal to W2 into RT divided by pi into V. W2 is the number of grams of the solute dissolved in V liter of the solution's temperature T. Pi is the osmotic pressure. So naturally it is seen that if we can determine the osmotic pressure of a solutions of this known composition, then molar mass of this solute could be calculated, and it is a very common applications of all the colligative properties in which the molar mass of this solute could be determined. And now we are coming how this osmotic pressure of a solution could be determined. We have so many experiments for determining the osmotic pressure of a solution, but out of which I have chosen here one method which is Barclay and Hartley method. Barclay and Hartley method. This method is very simple and very quick, and no chance of diluting these solutions. Means additional pressure equal to osmotic pressure is added on the solution side in order to check this osmosis. So from the very start, the osmosis or the flow of the solvent is checked up, and so no question of dilution of the solution. The experiment, the sketch, rough sketch. This is the porcelain cylinder placed horizontally, and both sides are blocked by a cord here, and in this case one capillary is added, and this wall of this porcelain porcelain cylinder is made of the made of the electrically deposition of this potassium copper ferrocyanide, so that these walls can act as this semi-permeable membrane. So here actually one thistle funnel is added in order to in order to enter the solutions. Here it is solvent. Here it is pure solvent, and the outer gunmetal cylinder, and in this case it is piston. Here the pressure gauge, and it is tightly sealed. Here is the piston in which this pressure have been added, and this annular space of this porcelain cylinder and the gunmetal cylinder contains this solution. Contains these solutions. So this is the solvent, and this is the solution containing the solute particles, and here the solvent meniscus is up to this mark. Now the excess pressure or additional pressure is added to this piston in the form of weight. This is pressure gauge. So weight is added on the piston of the solutions so that this mark or level of the solvent remains in its initial position from the very start of this experiment. It means that the pressure added here is quite sufficient or equal to the osmotic pressure, so that the flow of this solvent from this solvent side to the solution side is not possible. So the pressure gauge, this pressure gauge measures the pressure gauge measures the pressure which additional pressures are added on the solution side, and this one is the pi. So the experiment is very simple and very quick, and solution is not diluted. So this experiment, this Barclay-Hartley method, is very popular to determine the osmotic pressure of a solution. So however, nowadays various other osmometer are used which are very sensitive and give you very accurate value. Now I set one problem so that this equation could be utilized, and problem is at 25 degree centigrade 2.50 gram of a substance in 250.00 centimeter cube solution exerts osmotic pressure of 400 Pascal. This is a very simple. Temperature is given, weight of this solute is given, volume of this solution is also given, and the osmotic pressure is also given, determined by means of osmometer, and we have to calculate the molar mass of this substance. This is a very small problem. So we can put all these terms here. So M2, molar mass of this solute, W2 is, if we use say SI unit, since pressure is given in SI unit, so we can also use this, you can do these problems in SI unit, then 2.50 gram means 10 to the power minus 3 kg. And the R, the value of R is 8.314 joule mole inverse Kelvin inverse, and temperature is 298 Kelvin. And in denominator, this osmotic pressure is 400 Pascal means Newton meter inverse 2, and the volume is 250.00 centimeter cube means in meter 10 to the power minus 6 meter cube. 10 to the minus 6 meter cube. So all the terms, all this data have been put here, and now cancelled is like terms. This Kelvin inverse Kelvin, and joule means Newton and meter. Newton into meter is equal to joule. So meter, this one, and this one will be cancelled, and Newton also cancelled. Newton is the unit of this force. So all the terms are cancelled, units are cancelled, except 2.50 10 to the power minus 3 into 8.314 into 298 and divided by this 400 into 250.00 into 10 to the power minus 6. If we, and unit will be kg mole inverse. Kg and mole inverse. So if we do this calculation, then it will be 61.94 kg mole inverse. So this is the answer, 61.9. So this is the molar mass of the solute which have this data collected from this experiment. Now one thing I like to express here, this relation. Since it is colligative property, since osmotic pressure is a colligative property, hence the molar mass of the polymers, which is a very big molecule having the large mass, and the artificial manufactured polymers or artificial polymers are poly-dispersed, means molecules are having the different sizes, different molecular weights. So average molar mass for these polymers have been taken. So molar mass of these polymers could also be determined by measuring the osmotic pressure of these polymer solutions, and polymers are dissolved in a good solvent where the molecular chain of these polymers are partially or not entangled, or rather the solution behaves ideal. So all polymer solutions are generally non-ideal. So the polymer scientist Fleury has got this Nobel Prize on his work of this polymers, and Fleury have proposed one virial equation for this polymer solutions which is behaving as non-ideal. So in this case, the modification is that W2 by V into RT by M2. And this one actually, this is also concentration, and it is the weight concentration. Weight concentration means weight of this solute in grams dissolved per liter of the solutions, and this is expressed as suppose C dash. So pi equal to C dash into RT by M2, or we can write pi by C dash is equal to RT by M2. This relation is valid for Van 't Hoff's. This is the one form of this Van 't Hoff equation, and this equation is valid for ideal solutions only. And as I have stated, the polymer solutions are not ideal; they are non-ideal due to entanglement of these polymer chains from one molecule to with this. Of one molecule with the other molecule of this polymers in solutions. So for non-ideal solutions, Fori proposed that pi by C dash. Pi the osmotic pressure, C dash is the weight concentration, and this is equal to RT by M2 plus A C dash plus A 1 C dash square, means the virial form of this weight concentration, this term. Both this term is intensive property. This left hand intensive property, this could be expressed in the virial form. A and A1, these are the virial coefficients. If we take the several polymer solutions in good solvent of lower concentration, so then C dash square could be neglected. It is since C dash is very small dilute solution, so square term you can neglect and cut off here. So this is the relations. This is the relations. We can cut off here, and this Fori equation is like that. Now we can prepare these polymer solutions of several various concentrations of these weight concentrations at this lower end. So this collected data is plotted in a curve. Here pi divided by C dash, and here C dash. So this will form a straight line, and the intercept, this extrapolated intercept equal to RT by M2. So you can see from this plot, this extrapolated intercept will give you the value of RT by M2, and M2 is the molar mass of this polymer. So here this M2 is the number average molar mass of the polymer, and expressed as Mn bar. So this is all about here, and now the last one, I like to interrelate the four colligative properties of a solution through the value of x2, interrelation. So that if you know the one colligative property, then other colligative property could also be calculated. So this X2 is the bridge for interconnection, and X2 equal to del P1 by P1 naught relative lowering of vapor pressure, and it is equal to L vaporization bar divided by R TB naught square into del TB. This is another colligative property, and this one again L fusion molar latent heat of fusion divided by R and TF naught square, and here it is a TF colligative property, and this one equal to V1 naught bar divided by RT into phi. So you can see the different four colligative properties are connected by an equation, and if you know one, then other could be determined. In an examination, I have seen one question. They say, suppose delta P1 is to be plotted against delta TB of a solution. So in this case, you can see this delta P1 equal to this P1 naught into L molar latent heat of vaporization divided by R TB naught square into del TB. So this term within the bracket is exclusively the property of the solvent, and so if we plot del P1 versus del TB, then it would give a straight line passing through this origin, and slope would be equal to P1 naught L vaporization bar divided by R into TB naught square. From this slope you can calculate any one value if the other values are known to you. This is the slope. Y equal to mx. So this is all about the details of this colligative of this osmotic pressure of a solution, and also from I have completed all the four colligative properties in details. Now my next class will be the discussion about this abnormal colligative properties of this solution. Thank you all who are watching this video.